Okay, so let's scoot on. We're talking about logarithmic functions. So first let's give a definition. A logarithmic function has the form. Now the way you read this is y equals log base b of x. Again, log base b of x. It has this form if and only if its inverse is true. Now here's the deal. We just spoke about exponential functions. This log function is in the correct form if its inverse is true. Now here's the deal. This definition is going to show you like a shortcut of transferring a log function into an exponential function, and then clearly you can go in the other direction also. And I'll show you why the shortcut works later when we start solving these equations. So, in an exponential function, the first thing you always identify is the base, correct? Well, we just read log base b, so the base is b. And in an exponential function, your base needs a power. Your base needs an exponent. Well, the exponent is found by its little old lonesome on the other side of the equal to sign, which in this case is y. And it equals the only thing left, which is x. Okay? So this is how you can flip back and forth between log functions and exponential functions. Now, before we go any further, whenever we talk about a new function, we always need to know its domain as well as its range. So let's take a look at that. I would like to graph log base 4 of x equals y, or y equals log base 4 of x. So here's the deal. Remember those two bases we spoke about in the exponential functions? The common base, which is 10, and the natural base, which is e. Your calculators are both programmed with those bases. This is a base 4. Your calculator's not programmed with that. So in order for me to graph this log function, this format, isn't working for us. So we need to take it from a log format into an exponential format. So notice, first thing you identify in the base, which in this case is, good, 4. And the base always needs a power, which is found by its little old lonesome on the other side of the equal to sign, which in this case is y. And it equals the only thing left, which is x. This is the exponential form of this log function. And that's what we're going to graph, because I can plug numbers in there, no problem. And as a matter of fact, y would be the better variable to plug numbers in for. Don't you agree? Okay, so if y was 2, 4 squared is, good, 16. If y was 1, good, this would just be 4. If y was 0, 4 to the 0 is 1, excellent. If y was negative 1, that's right, you get that fraction of 1/4. And if it was negative 2, you get that fraction of 1/16, don't you? All right, now, if we take a look at the graph of this, remember, you graph the x's first. So this is the point 16, 2. So that's way out here in no man's land. And then you graph the point 4, 1, which is about there. And then 1, 0. And then a quarter and negative 1, and then a 16th and negative 2. And if I connect these dots, this is what my graph looks like so far. So here's a question for you. As you graph this function beyond, all the way out to positive infinity, what's this graph going to do? Yes, it's going to keep going up. Now, does it go up quickly or slowly? Yeah, in this case it goes slowly. In the exponential, it went up very fast. But in this one, it's going up slowly. So yes, it's still going to go up. It's just going to climb very snail's pace. Now, on this end of the world, do you think you're ever going to get any negative numbers for x? think about it. If I keep plugging in these negative y values, right? I keep plugging in negative y values. Is this ever going to be a negative answer? No. Is it ever going to be a 0? No. So we're skimming stones here, right? Just along the y-axis. Good? Okay. Now, I am going to graph a second one. And so, again, allow me some board space here. Let me get this gone. By the way, while I'm getting myself some board space, I would like you to look up the definition and the domain and range for that exponential functions that we spoke about in the last lecture. Why? Because I want you to see that they are truly inverses of each other, and then I want you to actually see what happens with the domain and the range and a few other things that we've gotten from the graph. And you'll see the benefit of the inverse functions. Now, I know I have not identified the domain and the range yet, so hang in there. I'll be back to that. I'm going to leave that up here, but I would like to graph one more function before we talk about the domain and range. Okay, so the next function I would like us to graph is y equals log base of a fourth power of x. Log base 1/4 of x. By the way, I said log base 4 of x over here, right? You hear that word of? Write this down. Of does not mean multiplication here. Of does not mean multiplication. X is a number, that's true, but log is not a number. It's an operation. It's not a number. So you can't say this is log times x. That's not it. This is the operation that you're doing to the x. All right. Now, same deal. Now I'm trying to find a log base of 1/4, which my calculator deals with only 10 and e. It doesn't deal with a 1/4, which means that's not the right format for us. So you guessed it, we've got to turn it into exponential. So remember, if you're going to turn to exponential, the first thing you identify is the base, which in this case is a fourth. And the base always needs a power, which is y, this thing all by itself on the other side of the equal to sign. And that leaves the only thing left, which is x. Wonderful. So I am going to use the same y values, and now I have new x's for this problem. Okay? So I'm still going to plug in 2. So 1/4 to the second. Good, that's 1/16. 1/4 to the power of 1. Good, that's still 1/4. 1/4 to the power of 0. That's still 1. 1/4 to the power of -1. Good, that's 4. And then 1/4 to the power of -2 is 16. So I'm going to use over here this graph still. This was problem number 1. Okay? So, or graph number 1. So let's look. Now I've got a 16th and 2. So 1/16 and 2. I've got 1/4 and 1. Okay, 1/4 and 1. I've got 1 and 0. I've got 4 and -1. And then I've got 16 and -2. So if I connect these 5 dots, this is what my graph looks like. So over here, this graph is going downhill, isn't it? Quickly or slowly? Yep, slowly again. Okay, and by the way, this is for problem 2. And over here in this end of the world, do you think you're going to cross this y-axis? Nope. This one is doing the same thing. It's just kind of skimming along the y-axis, not crossing it, not touching it. Good? With me? Okay, so let's look at the domain. The domain are my x's, and my x's are starting right here at the y-axis, and they're moving out to infinity, aren't they? Now the number they're starting at technically is 0, isn't it? But are you using the 0? Was 0 ever plugged in for the x's? Did we ever get an x of 0? No. So parentheses, and of course your infinity always gets a parenthesis. We never got a 0 for x. Okay, we got all these fractions, and these fractions are getting close to 0 for x, but we never got 0 for x, which is why you have the parenthesis. Now, for the range. So it doesn't matter which graph I look at, whether the pink one, which is the first problem, or the yellow one, which is the second problem. As I'm coming in from the bottom, both graphs are heading to negative infinity. One of them's heading quickly, the other one's heading slowly, but they're still heading down to negative infinity. And then as I move up, they're heading to positive infinity. Okay? Now, I did ask you to go back and get that exponential functions definition, correct? Do you notice the domain of the exponential function? That was negative infinity to positive infinity, wasn't it? Do you notice that's now the range for the log? The exponential function. Look at its range. What was its range? Yeah, its range was 0 to infinity, not including 0. Do you notice that's the domain for the log function? Here's the deal. These functions are inverses of each other. Exponential functions and logarithmic functions are inverses of each other, which means the input and the output switch, which means the domain and the range switch. That's the beauty of an inverse function. And by the way, these are one-to-one functions, okay? Every time I plug a number in for x, I get a single y, but each of these y's was only derived from a single x. So this is a one-to-one function, which means it has an inverse, and the exponential is its inverse, and the domain and the range have switched from the exponential. Now, a couple other things to identify. Do you notice on the exponential which intercept that it have? It had the y-intercept, yes. Today, we don't have a y-intercept, we have the x-intercept. So my x-intercept is 1, 0. Whereas your y-intercept for the exponentials, correct, was 0, 1. So it switched, right? The intercept switched and the x and y switched. Got it? Okay. Back to the exponentials. It had a horizontal asymptote, didn't it? That x-axis was its boundary line, wasn't it? Well, in this case, the x-axis is not the boundary line. The y-axis is the boundary line. In this case, I have a vertical asymptote, and it is the y-axis. And by the way, the y-axis is a line cutting through the x-axis at 0. My vertical asymptote for the logarithmic function is x equals 0, also known as the y-axis. Look at your exponential notes. That's right, it had a horizontal asymptote. That was the x-axis, and it was y equals 0. It switched again, didn't it? Domain and range switch, my intercept switch, my asymptote switched. The only thing that's remaining the same is the base. The base being a number greater than 1 tells me I have an increasing graph. My base being less than 1 tells me I have a decreasing graph. Are you with me? Remember all those things we did for graphing? They still apply here. If we tack on a +2, then this second graph is going to shift up 2 spaces. If we -1 on the x's, then this thing is going to go to the left 1 space. So just understand, all that stuff we do for graphing is exactly the same on logarithmics. Cool? Okay, so hang in there. I got some more information for you regarding logarithmic functions. Okay, so let's look at a couple of examples of switching an exponential to a log and a log to an exponential. So let's look at this first set of directions. They would like us to write in exponential format. So clearly I have a log format because it says log base 3 of 81 equals 4. Now, if I want to switch this to an exponential format, the first thing I need to identify is your base, which is 3, excellent. And the base always needs a power, which in this case would be 4. and it equals the only thing left, which is 81. Now, you shouldn't need to ask anybody to verify if this is true. The question is 3 to the 4th equal to 81? Yes, it is. So you know you did this one correctly. So let's look at another one. Now, same directions, write this in exponential format. So the first thing you need to identify is your good base, which is excellent 5. And the base always needs a power, which in this case would be excellent negative t, the thing that's all by itself. And it equals the only thing left, which is z. Now this one you can't really verify because all you have is one number. You don't know what anything else is. So you have to be certain of your knowledge of transferring from a log format to an exponential format. Good? Okay, let's look at these directions. They would like us to write this in a log form. So let's look at this first example. So 4 to the negative second power equals 1/16. This is in exponential format, but they want us to write it in log format. So the first thing you need to identify, or actually before you identify anything, the first thing you should write is, yeah, if they want it in log format, maybe the first thing I should write is the word log. And while I'm writing the word log, I think I'll put the equal to sign in there at the same time. Now the first thing you identify after you know you should be writing the word log is your excellent base. And that would be 4. That base goes by the tail of the g. And the next thing you identify is the, power. Just like I did over here, you're going to identify everything in the same order. Except you're writing it in a different form, so things are going to go in a different place. But the order remains the same. The base first, the power second, which is negative 2, and that power goes by its little old lonesome on the other side of the equal to sign. And then you write the only thing that's left, which is, good, 1/16, and that fills in this gap right here. Cool? Okay. Got a second one for you. Okay. So, I have no idea what M and K are, but you know what? So be it. But they still want me to write it in log form. So the first thing you should be writing, excellent, is log as well as the equal to sign. And now we're able to start filling things in. The first thing you identify is the excellent base, which is m, and that always goes by the tail of the g. The next thing you identify is, good, the power, which goes by itself on the other side of the equal to sign. And last but not least, the k, which fills in this gap right here. Cool? You with me? Okay, so hang in there. Got a couple more examples about logarithmic functions. Okay, so let's talk about the common log and the natural log. This is the same when we spoke about the exponential functions with the common base and the natural base. So if we're talking about a common log, remember the common base? The common base was 10. So if we're talking about a common log, the common log is going to look like log base 10. But a majority of the time they don't write that 10 in there. If you just see them write the word log and you don't see a base, that's automatically assumed to be a 10. So understand that. Log base 10, the notation would just be log, no base written. It's assumed a 10. Cool? Okay, the natural log. Remember the natural base? Yes, that was e. So the natural log would be log base e. But they don't write it this way. The majority of the time, I'd say a good 99.5% of the time. Now hear the words, what I'm saying. Hear what I'm saying. They'll write it as L N, log natural. Got it? They switched it around. Log natural. ln. When you see that, it means log base e. Cool? Okay. Now, get your calculators out. We're going to do some calculator work. I'm going to put some problems up, and you get those calculators out, and hopefully you can figure them out before I am done writing the problems I'd like us to figure out. And yes, figure them out to 4 decimal places. Okay? How about I rewrite number 1? There we go. Okay, now go for number 1. Okay, so did you get number 1 yet? So when I punched it to my calculator, I ended up with this answer. I hope you did too. When I punched number 2 into my calculator, I ended up with be careful, right? You have to punch log versus ln. No base here, right? Means base 10. So you got to find that log key on your calculator, and you have to punch the ln key on the calculator for number 2, right? Okay, so number 3, did you get it yet? What? You got an error? Why would you get an error? Oh, wait. What? Okay, back just a minute or 2 ago. What did we say the domain of a log function was? The domain of a log function was from 0 to infinity, not including 0, huh? And I'm trying to take the log of a -3. Is -3 in the domain? Nope. So if -3 is not in the domain, can you take the log of it? Nope. This does not exist. Or DNE for short. Cool? Haha, you're like, you tricked me. What can I tell you? You're going to find this in homework. You might as well say it here. Okay, number 4. Wait, what? You got another error? What? Okay, what's the domain of a log function? 0 to infinity, including the 0? Nope, which means I can't take the natural log of 0 because it's not in the domain. Which means, yep, you said it, DNE does not exist. Cool? Does this make sense? Okay, hang in. Okay, so let's do some solving of some simple logarithmic functions. Now notice the directions say to solve, but they say to give an exact answer. You're like, well, what does that mean? That means no calculator. That means no decimals. Remember that. Give an exact answer means no calculator, no decimals. So stay off them calculators. Okay, so here we go. I would like to solve for x on problem number 1. Now, I'm trying to get to the x, aren't I? But I can't get to the x because what's in the way of me getting to the x? Yeah, this log. And this log base 4 is actually in my way because this is all one unit, so to speak. Now, remember the shortcut, right? They said take the base to the power and it equals the only thing left. Well, let me show you why that works. Okay, so what's the inverse of a log function? Excellent. It's an exponential function, but it's the inverse only if the bases are the same. So here's the deal. If I take this log function and I take the exponential and raise it to each side, this is now an exponential that I'm taking of a log and the bases are the same. What's going to happen here? Yes, they will cancel out, which means in this case, what will remain on that side is just x. And on the other side is 4 to the -1st power, which would be 1/4, as we have realized with negative powers. Remember what the shortcut told us. The shortcut said take the base, which was 4, raise it to the power, which was the only thing on the other side, and equaled what was left. It's the exact same thing as what we did. This is why the shortcut works, because we are technically raising both sides with a base of 4. So I'm using an exponential base 4 to cancel a logarithmic base 4. Are you with me? Okay, now some of you may actually like doing it better this way, because you're like, okay, that makes more sense to me than just like arbitrarily moving things around. Even though we're not arbitrarily moving things around, I know it may seem like it. So I suggest you work out this way then, right? Okay, so let's look at number 2 over here. Number 2, I'm trying to solve for x. Well, but they won't let me use the calculator. So this log is still not working for me. Are you with me? It's still not working. So here's the thing. I am going to take the exponential base 3, because that'll cancel the log base 3. And I'm going to raise both sides so it has a base of 3. So exponential base 3 of a log base 3, what do? Good, they cancel. Which means on the left side, what remains is 27. On the right side is 3 to the x. Yep, there's that exponential. Get the bases the same, so this is 3 to the third equals 3 to the x, which means, yep, x equals 3. Good? Okay, look at number 3. You're like, wait a minute, the base is x, so I am going to take an exponential base x on both sides. Got it? Because that'll cancel the log base x, which leaves me with 16 equaling x to the power of 4. That's interesting, isn't it? Okay, so problem number 2, once I had 27 equal 3 to the x, I had to get the bases the same so I could figure out what the exponents actually were equal to, right? Well, this one is the same principle, but in reverse order. I want the 16 to be rewritten so I have a base to the power of 4, just like the x has the power of 4. Because once I've got that, then I know what x will be equal to. So what is it? Good. 2 to the power of 4 is 16. And that would equal x to the power of 4, which means in this case, good, x equals 2. Loving it. Does that make sense? Okay, last one over here. Yep, same deal. Base of 2 to both sides, so it cancels the log base 2 out. And we end up with x plus 1 equaling 2 to the negative third power. What's 2 to the negative third? Good. X plus 1 equals, that's right, 1/8, right? You got to minus the 1 from both sides, don't you? So you have x equaled 1/8 minus 1, and yes, I'm expecting you remember how to subtract fractions, will give you a negative 7/8. Cool? Does this make sense? Good. Understand the basics of solving these logarithmic functions. And in the last lecture of solving exponential functions, the basics of them. Because in another lecture, we're going to get to some problems that are a little bit more involved regarding the setup of them for exponential and logarithmic functions both. But for now, you have fun with this stuff, and I'll catch you on the flip side.